Know what this is? It's a man talking to a machine.
Charges to Area 4.
And this is a machine talking to a machine. In a short time, we've come a long way. Communication between people is only an electronic impulse away. As man developed, he had to have contact, to trade, to travel, talk, and do business over longer and longer distances. And today, we must speed up our recognition of change. The pace grows swifter. The minutes crowd more closely.
Going to the office, in this case traveling entirely by cable, talking to co-workers, attending a meeting. For individual work, the computer retrieves information or documents and aids in calculation and analysis.
What seems on the surface to be a technology of isolation may in fact be a medium for reintroducing the individual to the needs and pleasures of community involvement.
Living in a complex modern society, this will be in a compact form in his own house. He'll have a television screen like these here and a keyboard, and he'll talk to the computer, get information from it, and he'll take it as much for granted as we take the telephone.
Welcome to Future Human, the series, the podcast where the team here at Silicon Republic explores the future of everything. I'm Anne O'Dea. In this episode, we're looking at quantum computing and the whole universe of quantum physics. This series is made possible by our presenting sponsor, Hays, that's Hays, is the world-leading expert in recruitment and workforce solutions, specialising in the professional and technical sectors and skills. Thanks to their support, the rest of this episode will be totally ad-free. To access great advice and insights, visit haztechnology.com/blogs. Quantum computing isn't just about a new type of computer, it's really a completely new way of thinking about computing. For decades, classical computers have powered our world, but now we're at a very interesting stage in the history of computing, where we may see in our lifetimes a complete paradigm shift to quantum. Our expert guests will help define quantum computing throughout this episode, but here's what you need to know to get started. Quantum computing is a new type of computing based on the principles of quantum mechanics, an area of science that describes how the universe works at atomic and subatomic scales. And this work has answered a lot of fundamental questions we had about physics, chemistry, biology, and we've been able to use that knowledge to develop new technologies like lasers, MRI machines, and yes, quantum computers. As often is the case in tech, there's a certain amount of hype around quantum computing, but is it justified? Will quantum computers solve complex problems that have been out of reach for classical computers? Will they help us tackle some of the big environmental and public health challenges we face in the coming decades? And on the other side, will they create new challenges, particularly when it comes to cybersecurity? To help us unpack all of this, I spoke with somebody who is truly at the forefront of quantum research globally. Seamus Davis is a physicist, and he's the first Irish recipient of the very prestigious Buckley Physics Prize. If you haven't heard of the Buckley Prize, 18 previous awardees have gone on to receive the Nobel Prize.
Weavers used to use punch card control systems to operate their looms hundreds of years ago. So it's the same logic. You have some classical object. It encodes a series of instructions. As each instruction is delivered to the machine, it carries out that step, and you end up with some cloth or, a number or something. That's how classical information technology works. Now, in silicon, it works by having these logical procedures fabricated into the chip. So in a computer, you deliver a number, and the processing steps are already hardwired into the chip using Boolean logic. So when the clock ticks, the chip carries out whatever it's supposed to do with the number and spits out the answer. And in your desktop computer, if you have one CPU, it happens several billion times per second. And modern computers have up to 16 CPUs, so maybe up to 100 billion times per second. And that's why they're so useful, because they're fast. It isn't because each thing they do is particularly exotic. It's just because they can do a lot of things very fast. Okay, so quantum computing doesn't use that classical logic of an object receiving an instruction and proceeding to carry out as ordered. Quantum mechanics isn't deterministic, so it involves objects being in two states at the same time or more. And because of that physical fact, the laws which control how the instructions are carried out are completely different. So people are trying to build devices where you could hardwire into the device a sequence of quantum mechanical instructions. Then you deliver a number to the device, it carries out the calculation, and it spits out the answer. And that makes it sound as if there's no difference between the two technologies. And at the level I just explained, that there is no difference between the two technologies. Where the difference comes in is because in quantum mechanics, you can have objects be in many states at the same time. So instead of presenting one number to the input, if it was a 64-bit quantum computer, you could, in principle, submit 2 to the 64 numbers to the input of the calculation at the same time. So it's massively parallel, exponentially parallel computing technology in principle, and not even in principle, it's demonstrated now. You can buy a quantum computer. They exist, they work. And the promise is that exponentially faster computing will be the product in the future, which we'll get from this technology.
And I suppose then just to talk briefly about what are the areas that are going to benefit when we do really have more widespread quantum computing?
Designing biomolecules, designing a new protein for operating the human body, completely impossible now. Or global logistics at the scale of individuals or individual vehicles, that's completely impossible. Investment control at the scale of individual flows of money between people, that's completely impossible. Understanding, predicting, and controlling the climate, controlling our data flows around the world and understanding the national security implications, predicting and controlling the ecosystem in the future. And, those are the simple ones. You could imagine attacking the problem of trying to understand how does the human mind work. Now, there's plenty of philosophers who will tell you that no scientist will ever be able to address that question, but I'm not in the same camp as those guys. I think problems are tractable, and someday we will have enough computing power to be able to understand how the human mind works. So it's all those profound mysteries and grave and difficult problems that we can't solve now, which in principle could be solved by computers which are 1 billion times faster.
I'm fascinated. Like you hear regularly about so-called breakthroughs in quantum computing. Tell me where you think it is at now and how far away, on a very basic level, how far away are we from relatively widespread use of quantum computing?
Venture capital, VC investment in quantum computing has started to turn down. It's diminished by about 50%. And I'm not a business person, but I'm guessing that the reason is that they're not reaping the profits within 2 or 3 years of when they invest the money. And, that's fair enough. It's a business decision, but we're dealing with physics and quantum engineering challenges here, which have already taken half a century to get to this point and might take a long time to come to the point of fruition, if fruition is a desktop, room temperature, high-power quantum computer. So at that level, I don't know the answer. And it appears to me like companies are beginning to think that that answer is nowhere over the horizon. Now you can look at the different side of the coin. In chemistry and physics, dozens of important fundamental problems have already been solved by using the quantum computers that we have. And of course, that was true for classical computers in the 1960s. So maybe we're in an analogous situation now. They work as advertised. They produce amazing results. So scientists are already benefiting greatly from the existence of quantum computing, and that bodes well for the future.
Tell me a little bit about the work you're doing in quantum.
I'm not a computer scientist. I'm a quantum physicist. And so we focus on discovering and understanding macroscopic quantum materials which are required for quantum technology, right? You can't use silicon to make quantum computers. You have to change to a new set of quantum mechanical materials. So we focus our attention on the very fundamental question of finding macroscopic materials that have quantum mechanical properties, which will be technologically and eventually economically important in executing this technology. And number one on our list is high temperature superconductivity, I think, as you know well, because the leading quantum computers we have in the world now are superconducting. I think IBM has 1,000 qubit superconducting quantum computer now. And they only work at temperatures so close to absolute zero that they're basically at absolute zero. And that's not very useful for a desktop computer. So what we need is high temperature superconductors so that superconducting quantum technology can be implemented under ambient conditions. Well, no such materials exist. So you need people like me to contribute to the search for those materials, their discovery and understanding.
And are you optimistic about, well, I mean, you clearly believe you can do it.
It's important to understand quantum computing is a relatively small sector of the total promise of quantum mechanics for economically viable utility. There's all kinds of other applications, quantum sensing, quantum cryptography, quantum simulation to design new materials, just all kinds of other stuff, which are also accelerating very quickly. So if you ask me, will the whole quantum technological and economic combination, will that be productive during the 21st century? Will it be successful? Will there be companies? Will there be jobs? Will there be important scientific and economic applications? Absolutely.
I really like that idea about, to have people think around quantum and its use elsewhere and quantum mechanics. I mean, are there solid examples of that already that you could give us?
If you've ever had an MRI, you're inside a giant superconducting magnet, which produces an enormous magnetic field, millions of times bigger than the Earth's magnetic field, and it doesn't use any power supply. The current flows around the magnet permanently without any interruption because it's a superconductor, a macroscopic quantum device. And furthermore, when you hear the MRI firing, ding, 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 that's a bunch of radio frequency pulses which are being sent to the spins in the nuclei in your body. And those spins are undergoing a purely quantum mechanical process and spitting out the signal, which is then converted into a picture, hopefully, of your health. So MRI is basically 100% macroscopic quantum mechanics.
Beautiful example. You mentioned quantum cryptography. You do hear people talking about, security risks when quantum kicks in, and if people use quantum for decrypting what we already have. Tell me a little bit about your thoughts on that, please.
There is a theorem which has been tested by experiment, which shows that if you use quantum entanglement to encode information to be transmitted between two people, the transmitted information can be decrypted, but it can never be decrypted without you knowing that somebody was spying on you. So there's a way of making sure that nobody is listening to your communication. And if they're not listening, you can guarantee that it can never be decrypted. And, that's been demonstrated now very reliably over almost 2 decades. And there are commercial companies that sell photonic quantum encryption system, and they're used in some of the biggest banks in the world for the key transactions. So there's little or no doubt that quantum encryption applications will grow in their importance in the future. You could imagine a future date when your iPhone has quantum circuitry inside and you want to send a very private message to somebody else, and it's quantum encrypted so that in principle, nobody can ever break it. So that's a perfectly at least conceivable application, and the high level of that application already exists. Now, the other side is that there are algorithms which plausibly could break the classical encryption code that we use for all of our data storage, all of our commerce, all of our medical records, everything. And also national security. Ireland didn't worry much about national security in the past, but they do now. I can assure you it's quite serious because we most of the data, a large fraction of the data in the world is actually in Ireland, right? So it's a very serious issue. So people are afraid that quantum decryption attacks would become something which would be possible by large-scale quantum computers. And that is motivating national security people to pursue quantum computing and also quantum defenses.
And just on a global scale, let me give you the example of everybody jumping in to learn all about AI because everyone's talking about AI. What about quantum? Are we preparing the talent for the future? Are we focused enough for, a future of quantum mechanics and potentially quantum computing in your view?
Many countries now are establishing like a quantum computing center. There's a big one in Holland. There's several in the US. There's going to be a new one in the UK in Harwell. There's one in Switzerland, Israel, Finland. There's a big new one in Sherbrooke in Canada. So what you're seeing there is concentration of nationally funded research in one center. Now, if quantum computing would become commercial so that technology companies would require hundreds or thousands of quantum engineers to build and sell their devices, we're not educating half enough people, okay? The problem about that is we don't know when that's going to happen. So it's hard to make the decision of when to start educating. But I think we should steadily increase our commitment to education in that area, at least so that we don't get left behind.
Makes sense. It makes sense. So just very finally, what excites you most about the potential and the future when it comes to quantum mechanics?
Quantum mechanics is the fundamental theory of everything, and physicists and chemists and understand the quantum mechanics of small numbers of objects when they're interacting. If I give you 8 identical objects and they're all quantum mechanical, and I use the theory of quantum mechanics and I say, here's the interactions between these particles, what's going to happen, right? That's the equivalent of Newton's problem for the planets, okay? Take the sun and take 9, one of the planets was kicked off. Take 8 planets, right? And then solve the equations, and can you predict what's going to happen to all the planets? Well, yes, Newton solved that problem. Now, if they were quantum mechanical objects interacting due to quantum mechanics, and there's only 8 of them, that's a solvable problem even using classical computers. But suppose you took 1,024 interacting particles. That would be a very tiny protein, for example. And you say, solve the quantum mechanics and tell me what's going to happen. It's completely impossible. There is no way to solve a problem like that with a classical computer. But with a quantum computer, those problems are all tractable. And we have already, IBM had a big announcement at the end of last year saying they had made some important advance in fidelity and utility of their quantum computer. But if you find out what problem were they solving, they were solving the problem of a large number of little quantum mechanical magnets in 2 dimensions, and they solved the problem, which couldn't be solved otherwise, all right? So from the scientist point of view, it's already very successful and very exciting and very important. Now, if you ask me, how can you make money with something like that? I don't know. Call up IBM and ask them. I don't know the answer to that.
Well, funnily enough, we did talk to IBM because even though we have a long way to go, like Seamus said, quantum is already here and it's already being used. So I want to know how the big tech players are dealing with quantum, how they're preparing for the day when quantum computing is more widely accessible. I spoke with Kate Marshall. She's a research scientist, software engineer, and the Global Technical Ambassador Lead for IBM Quantum. As part of her role, Kate helps IBM's clients understand quantum computing and how it would impact their industries. So she seemed like the ideal candidate for this episode.
For me, quantum computing essentially describes a fundamentally different type of information processing whereby we can take advantage of the fundamental principles of quantum mechanics that you might have heard of, like superposition and entanglement. So what makes them useful to us? And in one sentence, quantum computing is the opportunity for us to use these quantum mechanical principles to create problem spaces that are infinitely more complicated than any equivalent classical space, and can begin to therefore solve problems that have been previously considered to be classically intractable or impossible to solve within any reasonable amount of time on even the most powerful classical compute resources. They generally sit in 3 broad categories of problems, and those are optimization problems, simulation problems, and machine learning problems. but they spread across multiple different industries, from financial services to material science, energy and utility sectors, and as far as healthcare and life sciences, and even retail.
As you can maybe hear, we didn't have the clearest of connections from my call with Kate, so we're only including a small section of it in this episode. But Kate and I had a fascinating conversation about the potential for quantum, and I highly recommend a read of our full interview there on the Future Human section of Silicon Republic. I was particularly interested in how IBM is exploring where quantum could have the greatest impact through collaborative working groups with quantum researchers and IBM clients who are expert on the potential use cases for quantum. In the past 2 years, there have been 5 of these working groups set up, meeting regularly to discuss the use cases and where quantum can provide benefit in the near term and in the future.
So, for example, some of these groups include healthcare and life sciences. So this includes involving organizations like the Cleveland Clinic and Moderna, where we're exploring applications of quantum chemistry and quantum machine learning to challenge various different molecular discovery and drug discovery applications, and even using quantum machine learning informed pipelines to be able to anticipate the risk of different patients following surgery.
I do love that idea that these really enormous societal problems like climate change, I mean, I presume it is one of those places that quantum could really help with crunching huge amounts of data. Just tell me your own thoughts on that, if you don't mind.
That's sort of a common misconception about quantum computing, that it's really good at dealing with large amounts of data. It's not necessarily that it's really good at dealing with big data problems, but actually that it's a potential way that we might be able to extract more or different information from noisy but small data sets. So it's definitely something that a lot of clients are interested in with regards to sort of specific applications on the sustainability and climate area in general. We have worked in the past with various different companies on the development of efficient battery materials that, if used in a car, could travel longer distances and could take less time to charge.
I suppose, with any technology, there's always the fear and the concern around risks and everything. What about that idea of the risks and challenges of the quantum age?
So with a sufficiently large quantum computer, it is theoretically possible to break industry standard encryptions. And such a computer does not currently exist, but the decryption could leave huge amounts of data exposed. And it's a real and very underestimated security threat in some people's opinions. However, it's also really important to remember that there are steps that clients can take today to ensure that their data is quantum safe. And this really is about choosing a problem on which to base future standards of cryptography, whereby even quantum computers will find that problem sufficiently hard so that data remains safe. And the threat does exist today. Many people might say that, well, the computer of sufficient size doesn't exist, then I don't need to worry about it until that becomes a reality. But of course, a malicious actor could steal data today to be decrypted later. So the threat is very real right now.
I mean, are you excited about the quantum future, and what excites you most about it?
I'm extremely excited about the future of quantum computing. I think I'm probably most personally excited about the journey of how we get there. I think there's lots to learn from the other fields, such as in AI, so that we can make sure that when it comes to quantum computing, we're making this a technology that's democratized in the right way, that's deployed ethically, and is being used for ethical and sustainable applications. And I'm most excited about seeing what else comes out of the journey between now and that endpoint, and excited to see how we approach it as a global research community as well.
Like Kate, I'm very interested in how we might approach the development and use of quantum computing as a global community. How will we collaborate across research, business, education, health, and all the sectors likely to be impacted by quantum to ensure it benefits all of society? And I think an important first step in that process is ensuring that we all have a decent understanding of all things quantum. So this isn't just about training the next generation of scientists and technologists, vital and all as that is. It's about supporting a broader understanding of quantum that spans academia, business, and indeed the wider community. There's a growing effort out there to demystify quantum technology, so I was keen to chat with Katarina Foti in Helsinki about her work at Algorithmic and the QPlay Learn initiative, which tackle exactly this challenge.
I'm Katarina Foti. I'm a postdoctoral researcher at Aalto University and in Finland, in Helsinki, and in Algorithmic, a startup developing quantum software for life sciences based in Helsinki. And I'm coordinating QPlay Learn. That is a project and an online platform related to the outreach of quantum science and technologies. As Aalto University, I'm also part of Institute Q, which is the Finnish Quantum Institute.
Tell me more about this and tell me more about the importance of outreach. I think it would be fair to say that the general public don't really understand quantum a lot of the time.
It's totally fine to be initially scared by quantum physics, but I and also the team with whom I work, we are really convinced that the beauty of quantum physics and the potential of quantum technologies can be told to everyone, regardless of their age and background. We might be on the verge of what is famous as the second quantum revolution, playing a very important role for many of the main challenges that we have to face as a society in our time. So from energy to healthcare, for all these big challenges that we have ahead, quantum technologies might play a very important role. So I think it's very important that many stakeholders become part of this because so far quantum technologies have been, let's say, the subject of a small cohort of people. Only experts in quantum physics and people with a physics background have been involved in the development of the theory, but also of the application and the technologies. And now the situation needs a change. We are seeing many of the new master curricula focusing on quantum technologies popping around everywhere. But we already know that academia alone will not be enough, in the sense that, of course, it's fundamental and it's important because in order to have, let's say, the proper solid background in quantum physics, the academic path is the path that people have to follow. But since these challenges are so big, we need much more than just quantum physicists because we need much more expertise. So if we have to take into account also biologists, mathematicians, business experts, medical doctors, chemists, engineers. And if we consider even the stakeholders of the potential application, the list is even longer. So I think it's fundamental to involve many people in this.
I love that. That's amazing. And if you don't mind, tell me a bit more about the startup, Algorithmic.
So Algorithmic is a startup that has its headquarters in Helsinki. And the mission of the startup is bringing quantum to life. So it's a startup focusing on developing quantum software for the life sciences. And the team is made of experts with a quantum physics background, especially quantum information background, but also quantum chemists and this kind of people. And QPlay Learn is the outreach project of the startup. So since the very beginning, and this is something that I really love of our startup, because since the very, very beginning, at the early stage of the startup, when we were just a few people, this outreach mission and this quantum literacy at large was something that was really precious from the very beginning for us. And since then, it's a joint project between Algorithmic and Institute Q.
Amazing, fantastic! I love the sound of that. My gosh, we should have something like that in every country. So just to ask then, just that last question, how do we create a flourishing quantum ecosystem, in your view?
I think that we need many different stakeholders. And to do this, I think the crucial point is to create connection. So not only between academia and companies, but also between citizens and schools, policymakers, so really society at large. In fact, when we speak about quantum education, we don't mean only academic education, but not even school education, but really something that can involve the kids in the schools, but also the CEO in the companies, the executive teams, the policymakers, business leaders. We, of course, adjust the content to the target audience that we are addressing with each project. Our, let's say, philosophy, our method is always the same. And it's based on this idea that intelligence is diverse. And so we have developed this 3-steps method based on 3 phases that we have in mind that are play, discover, and learn, respectively related to intuition, understanding, and formalization. So the idea around the intuition phase is that people using playfulness, engagement, even video games, are kind of attracted from a specific concept. And then there is the understanding part where avoiding as much as we can the formalism, so the math, we try to describe a physical concept using descriptions, easy to follow explanations, and when we can, based on experiments, so on what we see from the physical world. And then the formalization comes, so where the math, the proper language of the theory of quantum physics enter the scene. And the idea is that according to the preferred intelligence, each learner can choose where to start and then eventually explore the other sections, let's say, and there is no specific order. And to do this, we have this idea in mind of creating multi-level educational resources. Multi-level because they allow all the path from the intuition to the formalization. And we think that this kind of resources, with this idea of building a multi-level education, can help us in avoiding misleading analogies and oversimplifications that are quite big risks, especially when it comes to quantum outreach and quantum education in those contexts where the proper formulas of the theory mathematics cannot be used. And so, yeah, this is, let's say, our approach, no matter who is the audience, if a kid in a school or a CEO in a company.
Why is it so important, what you're doing and getting that literacy?
When it comes to specifically to quantum physics and quantum technologies, I think it's important because quantum technologies might really play an important role. They have a disruptive potential. And I like that you really have to shift a bit from what we are used to grasp what quantum physics is teaching and showing us. And that I really, really like it.
And that is the paradigm shift with quantum. Like Katerina said, it really does mean a shift in how we actually think. So whether you're planning to delve into all things quantum computing or you just have a passing interest, I hope this episode encouraged you to learn more. At Silicon Republic, we try to stay abreast of all the significant developments in the field, so do keep an eye out for the latest on siliconrepublic.com. But I'd also encourage you to check out some of the resources we mentioned in this episode, like qplaylearn.com. That's the letter Q, the word play and the word learn.com. Or for the more technical among you, why not check out IBM's Qiskit platform, an open source software development kit or SDK for working with quantum computers at the levels of circuits, pulses and algorithms. It's a remarkable resource, and that's Qiskit, Qiskit. Just pop it in your search bar. As I say, I would encourage everyone to get themselves up to speed on the subject, because it seems we're well past the theoretical here. It's just a matter of when and not if we see quantum computing hit the mainstream. This series is curated by the Silicon Republic team and produced by Sean and Morris. The interviews were conducted by myself and Silicon Republic editor Jenny Darmody. The podcast is part of Future Human on Silicon Republic, and for more great content, from filmed fireside chats to deep dive articles, visit siliconrepublic.com future-human. Thanks again to our series sponsor Hayes, the experts in recruitment and workforce solutions.